Okay, at the core of linear regression is this method of least squares. So we learned that the standard square error statistic is the sum over all of the data points that we have with the actual observed value of y minus what the model would predict for the expected value of y at that point. And then we take the difference between those two things and we square them. And so this is the residuals, the sum of the squared residuals, if you will. And we can go through and we can imagine those residuals as these vertical lines between our model prediction, that's the diagonal line here, and the actual data. And sum of square errors is the sum of squares method is trying to find the line that minimizes the sum of those squared residuals. Okay, so in order to do that, we just take this SSE statistics, sum of our square errors, and we differentiate it with respect to beta 0 and beta 1. And when both of these two derivatives should be 0 at our optimal estimate for beta 0 and beta 1 hat. So notice that these beta 0 and beta 1 are themselves statistics actually because they will change every time we consider a new set of data for this problem, right? So that's important to remember, is that our best fit coefficients are themselves random variables. Okay, so the equations for beta 0 and beta 1, we can write down these coefficients. So let me return for just a moment to this. So you notice that this big ugly thing is actually just a polynomial when you look at it in terms of beta 0 and beta 1. So specifically it's a second order polynomial in those two variables. So we have now that those derivatives turn out to be pretty easy to do, and what you get, so I'm skipping some algebra, just basically grouping terms here, gives you all the terms that depend on beta 0 that come out of this first equation turn into a factor of n times beta 0 plus beta 1 multiplied by the sum over all of the independent variables xk. And that should be equal to the sum over all of the observations y sub k. And we can also collect terms in this second equation. The derivative with respect to beta 1 gives this equation here. Okay, so notice that this second equation now involves terms that have the independent variable squared. So that will be related to the variance in the variable x across our data set. And this one will be related to the covariance in x and y across our data set. And it's sort of intuitive that somehow this information has to come into the problem, right? Because that is going to tell us something about the degree to which changes in x are predictive of changes in y, is what the covariance is telling us. So these two equations are actually linear equations when you view them as with having beta 0 and beta 1 as the unknowns. So we can write these in matrix form, and just noting that we can write this sum as n times this average value of x, and likewise we can write this sum as n times the average value of y across our data set. And likewise for the covariance, we have x times y averaged across our data set. So this ends up being a factor of n times this thing that you see written here. And we have also the ability to write the squared independent variables summed, that by this identity is just n times the average of this x squared variable. Okay, so writing all of these things using that notation gives us this more compact set of equations, quite easy to write down now. And you see that in the first equation, that is looking across the top row of this matrix equation, we have a factor of n, a factor of n, and a factor of n here as well. Those all cancel. And likewise in the bottom, the factors of n all cancel away. So everything, all the coefficients and all the vectors over here on the right can really be expressed as things that only depend on the averages of your data set. And so doing that gives you this new simplified set of equations with this very simple matrix here on the left, acting on your your beta 0, beta 1 vector, and that's related to this easily computed vector of known quantities on the right. Okay, so now you could just use Cramer's rule, or you can invert this matrix by any other means that you like. What you find is that beta 1 is given by this expression, which is now recognized as the at least an estimate for our data set. I should probably have s's here instead of sigmas, because these are estimates of the covariance in x and y divided by the variance in the variable x, right? So I should really write s here, because these are sample standard deviations and sample variances and sample covariances, and not the actual variances and covariances. Okay, so then once you know the slope, right, if I know the average value of y that these have to go through, and I know the slope, I know how that's related to the intercept for those two things. It's just beta 0, the intercept, is equal to the average value of y minus this slope that we already computed, multiplied by the average value of x. Okay, so we can build now a rather contrived example. We'll take yk to be a function of xk, and so we have x values that range from 1 to 5. Nice and evenly spaced. This is a well-designed experiment in this case. Remember, we don't want to have a whole bunch of values here at x equals 1 and a whole bunch of other data points out here at x equals 5, and then basically interpolate across that long gap in the middle and hope that it's a line. Okay, that's a no-no. Don't do it. So what we want here is for our values along this x-axis to be fairly evenly spaced. Other things that appeared in the equations that we were just working with were the product of x and y, so we're going to need a column that has entries for those numbers, and a column for x squared. So in addition to our data for x and y, we have x squared and yk columns here. And once you know these numbers, of course, these are pretty trivial to go through and compute. So these are the averages. So the average of x across our data set is 3, the average of y across our data set is 2, the average of x squared is 11, and the average of xy across our data set is 7.4. Okay, so now from those numbers alone, we can compute that the best fit line has a slope of beta 1 equals 0.7. And the intercept then has a value of minus 0.1. Okay, so this is the equation that we get for our best fit line. And we can do all of this in Excel. So if you go into Excel and you ask to insert a scatter plot, it will put the points down here like this first. So those are the points x versus y, and you see initially it's just the points. But if I right click on those points and then go to add a trend line, select the option add a trend line, then it will tell me. It will give me a couple of options. It will ask me whether I want my trend line to be an exponential, a polynomial, logarithmic fit, all these different options. Here we're doing linear regression, and we'll just put a line through these points. And a couple of options down here are useful. You can display the r-squared value on the chart. We will learn that r-squared value is actually the square of the correlation coefficient between x and y. The closer it is to 1, the more perfectly correlated these two variables are. We also find that that what's often useful is to display the actual best fit equation on the chart. So this is actually where you get the coefficients out of Excel. If you don't click this option, it'll just put the line there and not tell you what equation it used to get that line. So I generally like to click both of these two values. And then you know, in some cases you might suspect, for example, for your null hypothesis, that the intercept is actually 0. And so you can restrict your fits to pass through the origin for those cases. Okay, so Excel can do a lot more things, and we'll talk about that in a few bits, maybe the next presentation. But this is basically your plot of y values versus x values, the blue data points here. And this is the equation. Notice that Excel came up with exactly the same equation that we did, a slope of 0.7 and an intercept of 0.1. The r-squared value, we will talk in detail about where this comes from when we talk about ANOVA. And this is the best fit line. Okay, so it looks pretty good. Obviously, there are some residuals here, but you can see that these two variables are related to each other. Okay, so we have a We have a little bit of time left, but I'm going to go ahead and break here and start the next lecture on analysis of variance, ANOVA as it's commonly called.